Welcome! In this lesson, we will turn a real production story into math, then into GAMS. We will decide how many sneakers and sandals to make at 4 plants, meeting demand at minimum total cost. I will go step by step: inputs, decisions, objective, constraints, and GAMS. This is the problem. And in one sentence, we can say that we must meet demand for sneakers and sandals and spend the least money. Money here means unit production costs plus one-time setup cost when a plant produces a product. Plants have capacity limits, and plants 2 and 4 can produce only one product each. These are the numbers, and we have 2 products for plants. Each product plant pair has a capacity, a setup fee if we decide to make that product there, and a unit cost per pair produced. Demands are fixed, so we have 80,000 sneakers and 9,000 for sandals. We can say right here all the sets and data already written, with the sets and the 2 tables with the respective demands. Before passing in writings the variable, we need to build a new parameter that set the real variable cost for sneakers and sandal. In the first case, we set the base price to 25 for sneakers and sandals to 20. And then we set the condition appropriately according to the ones that we are going to see here. For plants 2 and 4, their respective price are 5% more expensive than the relative price. So for sneaker, the total price is 26.25, and for sandal is 21. And then we are going to adapt these prices according to special rules that we will see later. We have 2 decision variables. The first is xpn, that must be greater equals to 0. That is the quantity of product P made at plant N. And then we have ypn that belongs to either 0 or 1. This is the setup used at plant N for product P, where 1 means that we produce it and the pay setup. About the objective of the model is to minimize the total cost zeta, and it's divided into 2 parts: unit cost per quantity plus the setup fee whenever y equals to 1. The solver will choose x and y to make this as small as possible while meeting all the rules. The first constraint is to meet the demand exactly. The total sneakers made across all plants must equal 80,000, and same for sandals, that must equal 90,000. There are no shortages and no overproduction. The number 2 condition instead is that the capacity by product and plant. You cannot exceed the capacity of a product at a plant. If a plant 2 can make at most 2,000 sandals, the condition variable sandal at plant 2 cannot go above 2,000, and this is the condition that set the problem. Here is the math model, and here is the GAMS condition. Then we need to set another part that hits about the link between production with the setup cost. So connect x and y. If y equal to 0, the right side is 0. So x must be 0, and we can produce. If instead y equals to 1, the limit becomes the capacity, which is the natural maximum. This is a classical big M link using capacity as M. And the last one is, constraints number 4 is that only one product in plants 2 and 4 can be produced. Must choose one product only. These two inequalities force exactly that at the most one of the two binaries can be one in each of those plants. This is the condition ORD E2 and ORD E4, with the sum of the total product that are produced inside the plants must be less than 1. So the maximum amount that must be produced is 1. And essentially, here is a repetition of the model that we have built together with everything that we have done. So the last part, it's about reading the conditions that we have set with the x.l that shows the production plan by product and plan, y.l that shows which setup are active and which are not. Z.l is the minimum total cost, and as a sanity check, we can say that the totals over plants should be 80,000 for sneakers and 9,000 for sandal. No plants X exceed its capacity, and plant 2 and 4 only make one product. Then, in the problem, we have also a new kind of problem because we need to solve a second part. The second part is this, because we need to add that plants 1 and 4 cannot be simultaneously operative. And so, to solve this problem, we need to add plant active binary and constraints. So we need to add a policy. Plants 1 and 4 cannot be active at the same time. So we introduce a plant active binary that we will call AN. If any setup is used in plant N, AN equals to 1. Then force A1 plus A4 less or equals to 1. And this is the total condition. We can have an alternative that is written right here, but this is the simple way to solve that. In GAMS, we have the binary variables that we'll call the VUI, the equations with the constraints on plant 1 and 4, and the consistency between variables, between the binaries. Here is the conditions, and here is the total that must not be over the total capacity multiplied by 2. And that is exactly the model finished with point 1 and point 2 with a brief explanation from words to math to GAMS decision. This template works for many production and location problems. You need to just change the data tables and keep the structure. Thanks for watching. See you in the next video.